Hi all, welcome back. So as I mentioned in part 1, that in part 2, I'm going to talk about classification of loose links and an invariant, along with some future work direction. So before I start part 2, let's have a quick recap. So what we saw before that in an over-twisted manifold, we can have two types of knots, loose and non-loose, where loose knots have complement over-twisted and non-loose knots have complement tight. And at the end of part 1, we saw that Etnia's result, which coarsely classifies loose null homologous knots. By classification, I mean that loose null homologous knots can be determined by its classical invariance, that is TB and rotation number. And yes, it needs to be null homologous. So the question was, what about loose links? And it turns out that loose links can also be classified by their coarsely classification, of course, by their classical invariants. So this is my first result, which tells us that if we have two loose Legendrian null homologous n component link, and here by null homologous, I mean all the components are null homologous. So if the links are topologically isotopic, the TB and the rotation number are the same component wise, then they are coarsely equivalent. So the main idea of this proof, what is the main idea of this proof? They are loose, so the complements are over twisted, and if the complements are over twisted, then we can use Eliashberg's classification. So that is the main thing of this proof. So first of all, we need Eliashberg's classification. Second of all is, which I mentioned in part 1, Gom's result, that D2 and D3 can classify homotopy class of two-plane fields. And Eliashberg's classification tells us that over-twisted contact structure up to isotopy are nothing but two-plane fields up to homotopy. So combining those two results, if we can match D2 and D3, so basically we try to match these D2 and D3 of the complements. So match them. And third, how to match the D2 and D3. So here we have to use the relative version of Pontryagin-Thom construction. So this gives us, actually the relative version gives us a nice way to associate D2 and D3 invariant with framed cobordism classes of link. So these three things are the main tools of this proof. This is pretty technical, so I will not go into the details. So the next question is, what about transverse links? Well, this is pretty common in contact geometry, that we can prove something for Legendrian knots or links, and then use this nice relationship between Legendrian and transverse knots and prove it for transverse, which I did too. So as a corollary, I showed that if T and T prime are two loose n component transverse links, with each of their components being null homologous, if they're topologically isotopic and they have the same self-linking number component wise, then they are coarsely equivalent. Okay, so now we have this coarse classification of Legendrian and transverse link. The next is the invariant. So we want to define an invariant of Legendre and transverse links, and we want to see that if that invariant can tell us anything useful about looseness. So to define this invariant, we will use a very special tool, which is known as open book decomposition. So why open book decomposition? So before I say why open book decomposition, we need to know about open book decompositions and the definition. So an open book decomposition of a three manifold is a pair which consists of a fibered link and the fibration of the complement. And here I should mention that there is another notion of open book, which is known as the abstract open book. So this definition I mentioned here is for abstract open book, which is specified by a fiber surface and a monodromy map. And we can go back and forth between these two definitions. So there are ways to go between these two definitions. Now, how open book decompositions and contact structures are related. We say that a contact structure is supported by an open book if these two conditions hold. So these technical conditions are telling us that the fibered link, which is the binding of the open book, we want that to be transverse, which is the second condition. And the first condition is telling us that we have the fiber surface, which is the page of an open book, and the tangent vectors to that page appropriately approximates the contact structure. So whenever these two conditions are fulfilled, the open book and the contact structures are compatible. Okay, now why open books? Why open books are so important in contact geometry? This is due to Giroux's fundamental result. And Giroux's theorem tells us that for a fixed tree manifold, there exists this one-to-one correspondence between open books up to positive stabilization. This positive stabilization is an operation on open books, and contact structures up to isotopy. So this result is so important because this allows us to move between these two worlds. One is the topology world and the other one is the contact geometry world. All right. Now it's time to define the invariant. Okay. Before defining the invariant, which is the support genus of a Legendrian link, I should mention that a support genus of a contact 3 manifold was defined by Etnayer and Ozbakchi. And how they defined it? It's a minimal genus of the page of the open book which supports the contact structure, because one contact structure can be supported by lots of open books. And we know that all those open books are related by positive stabilization. We just pick the one which has the minimum genus. Later, Onaran, she defined the support genus of a Legendrian knot, and that actually naturally extends to support genus of a Legendrian link. So how this is different from the definition of a support genus of a contact 3 manifold is the same thing. We pick the minimal genus page of the open book supporting the contact structure. The extra thing is we want the Legendrian link to be on the page of the open book. And this is well defined because it's well known that every Legendrian link can be put on a page of an open book. Okay, so how this support genus is useful in detecting looseness. So suppose we have the coarse equivalence class of a null homologous loose Legendrian link, then the support genus vanishes basically. So if it's loose, then it can always be put on a planar page. Okay, how the proof works. Again, I'll give you just the main idea. The first step of the proof is that put the Legendrian link . on a planar page. And this is possible due to Onaran's result, where she showed that any Legendrian link in any three manifold can be put on a planar page. But be careful, this is a purely topological result. So the open book might not be supporting the contact structure we want it to support. But in contact geometry, there are tools which can make the open book supporting the contact structure we want it to support. That is, we can make it compatible. So using those tools, we can make the open book compatible. All right. So now we have an open book compatible to the contact structure, and the link lies on the page. The third thing is we want the link to realize every TB and rotation number. And in this third step, actually, we need the classification of Legendrian loose links. So we do not have actually isotopy classification. And that is why in the statement, I had to use the class, the course equivalence class. Okay, so we saw that if we have a loose Legendrian link, we can put it on a planar page. The obvious question is, what about the converse? So if we have a non-loose link, is this always true that a non-loose link will have support genus greater than 0? If it is true, then support genus can distinguish loose and non-loose links, and that would be great. But unfortunately, that's not the case. And here's why. So there are actually examples of non-loose links with support genus 0. And this is one example. On the left-hand side, we have the positive Hopf link. The blue and the red component together are the positive, is the positive Hopf link. And this is the contact surgery diagram again, because we do not have front diagram in over-twisted S3. And this is S3Z -1. And it's not also hard to see that why this is non-loose. On the right-hand side, we have the fiber of the open book, which supports this particular contact structure. And we can see that this link lies on the page. And the page is a disk with punctures. So this is planar. And so non-loose links can have support genus 0. Okay, so all of these results are about Legendrian links. What about transverse? Okay, now for transverse links, if we want to define a similar kind of invariant, first we want to associate a transverse link with an open book. Now for Legendrian link, it is a well-known fact that we can always put a Legendrian link on a page of an open book. For transverse, we have to work a little bit more. So this is this theorem telling us that if we have a transverse link in any contact 3 manifold, and then T is transversely isotopic to the sub-binding of some open book which supports the contact structure. And here, by sub-binding, I mean that I can make the transverse link parts of the binding. All right, so this theorem allowed me to define the support genus of a transverse link, which is again the minimal genus of the page of the open book, which supports the contact structure, so that we can realize the transverse link as a sub-binding of that open book. So it's pretty similar to the support genus of a Legendrian link. It's just that we have to realize it as sub-binding of the open book. So obvious corollary is that the support genus of a coarse equivalence class of loose null homologous transverse link also vanishes. And again, for the same reason as before, I had to use the coarse equivalence class and I couldn't use the isotopy class. All right. Next is the relationship between these two support genus. So we have a support genus of a Legendrian link and we have a support genus of a transverse link. So for a transverse link, if we take the support genus of a transverse link and then its Legendrian approximation also has a support genus, and these two are actually the same. You might ask that a transverse link can have lots of Legendrian approximation, because I mentioned in the part 1 that the Legendrian approximation operation is not well defined. So what about that? Actually, if we can show that a support genus is invariant of negative stabilization, then if showing the support genus of any Legendrian approximation is same as the support genus of the transverse link, proves it for every Legendrian approximation. And it turns out that support genus does not change under negative stabilization. So they are the same actually for any Legendrian approximation. Okay, next I would like to mention Onaran's result, where she proved that the support genus of a loose null homologous knot, Legendrian knot, is 0. And her result actually does not use the coarse equivalence class, but she used the isotopy classification, which was known. So the corollary to this result can be for transverse knot, that a loose null homologous transverse knot has support genus 0. Okay. Next question is how useful a support genus can be, because we saw previously that it cannot distinguish loose and non-loose links. So is there any other use of this support genus? Actually, non-loose, if you take a non-loose transverse knot and you apply this Legendrian approximation, you will always end up with a Legendrian knot which is non-loose. And this is due to Etnayer. This direction. On the other hand, if we start with a non-loose Legendrian knot and we do this transverse push-up operation like I mentioned before, the result is a transverse knot, of course, but it might not be non-loose. And an example is actually the unknot. So as I mentioned, non-loose unknot lives in S3Z -1, result by Eliashberg-Fraser. But they also proved that there exists no non-loose transverse unknot in S3Z -1. So if we take this non-loose Legendrian unknot and we apply transverse push-up, we will get a transverse unknot, but it has to be loose. So that's why sometimes this transverse push-up will give us loose knot, sometimes it can be non-loose. We do not know under which conditions it will always preserve non-looseness. But here is a theorem which just having like all these theorems together, like collecting all the theorems together. So if we start with a Legendrian knot whose support genus is already greater than 0, in that case, its transverse push-up will be non-loose. And this is actually not true for unknot. Unknot does not have support genus greater than 0. Its support genus is actually 0. And that's why it doesn't work for unknots. Okay. Next is future work. The obvious question, the first question is that can we strengthen the classification? Because it would be really nice to have a classification of links up to isotopy. And it seems like it's possible. And this will be a joint work with Khan and Chernov. And we think that their result about Legendrian and transverse knots can be extended for links as well. But again, with some extra condition. So we will have some extra condition. And actually, if this result, we can prove this result, this will also imply that the support genus of a Legendrian link is 0 for any loose link. So here, I don't need the course equivalence, which I used before, the course equivalence class. Here we can just use the isotopy class using that classification. Okay. Next question is classification and structure problems of non-loose knots, which is very interesting because classification of non-loose knots do not follow the same path as the classification of knots in S3 standard. Because lots of things which people use in tight S3 in the classification, for example, the Benny-Quinn inequality or say max TB, which comes from Benny-Quinn inequality, these do not work in over-twisted S3. We do not have a Benny-Quinn inequality. There is a Benny-Quinn type inequality, but that does not give us a max TB. We do not have a max TB in over-twisted contact manifolds. And so the classifications are, the techniques are a lot different. Now the structure problems, like we would like to know that when the non-looseness are preserved. So for example, connect sum operation does not preserve non-looseness, which is very surprising actually. So we take two non-loose knots and we do this connect sum operation, and we can find a knot which is loose. And think about examples, not very hard to see that this is actually connect sum does not preserve non-looseness. The next topological operation one should care about is cabling. So when cabling preserves non-looseness, does it always preserve non-looseness or not? So this is actually a work in progress, that when does cabling preserve non-looseness? And this is with Etnayer, Min, and Mukherjee. Hopefully, soon we will be able to find all the conditions when cabling will preserve non-looseness. And that's all I have. Thank you for listening.